Okay, greetings. This is the review session for the second midterm. It's in week 9. The deal is the same as before. It's in class. Bring a pencil and pen and a calculator. We'll supply the exam script and an equation sheet. The equation sheet will be exactly the same as what we talk about today in this. It's on each of Monday, Wednesday, and Friday, 8 o'clock. Probably start a bit earlier and run till 8:30. The material is the second third of the class. It starts off with our beginning with Bernoulli, conservation of mass and conservation of momentum, so 4.2 through to 7.3, I guess. And more importantly, for the scheduled exam, these are the 3 topics. So the first one is Monday, it's Bernoulli and free jets. The second one is conservation of momentum, linear momentum. And the third one is conservation of momentum rotationally. So 7.1 and 2 and 7.3. So the topical materials, Bernoulli, we know that we write Bernoulli between upstream and downstream, where we can equate the pressure, elevation, and velocity heads. We hope that we can define 5 out of the 6 parameters so that we can solve for the remaining 1. If we can't, if there are 2 parameters are unknown, then we can constrain it by mass rate in equals mass rate out in a stream tube to be able to solve with 2 equations and solve for two parameters out of the 6. The physical representation of Bernoulli is if you take flow down a pipe. I don't think we've talked yet about pump heads and turbines, but if we look at flow down a tube, you can look at the elevation head, the pressure head, and the velocity head as being those elevations relative to some datum, and it has to be the same upstream and downstream. And if we have energy put into the system and energy losses in the system, which we don't yet, then we have to deal with each of these. We write the equations along a streamline, so the streamline could be straight or it could be curved. It defines a stream tube, and of course the stream tube defines this conservation equation between mass rate in equals mass rate out of the stream tube. We've talked about relative velocities, so a boat moving at a velocity of the control surface, squirting out water at velocity w. To a static observer, this water looks to be traveling at a velocity vs because it's the sum of these 2 components. It's a vector sum, so it doesn't have to be just in the x direction. It can be a vector in the x, y, and z directions. Typically we will only use one, but this is the relationship that defines that. Free jets is on the test, so you should understand how those work. We've done it with the large tank assumption. Means that if it's a large tank, the velocity on the surface is 0 because it doesn't get drawn down quickly enough compared to the jet coming out of the bottom. You can write Bernoulli upstream and downstream, and if you solve that for the unknowns, you get a velocity out of the tank being square root of 2gh. H is the vertical height between the top of this along the stream tube. If water comes out at this velocity out of the bottom of the tank, it also comes out horizontally at that velocity or vertically upwards at that velocity, so you know what the velocity is coming out of the tank. If it's a question where you're looking to see how high it rises, you know that laterally it will keep on moving at the same component of the vector horizontally, but the vertical component of the vector, it will slowly rise until a peak, and the peak is given by the vertical velocity at this point here and the time taken to rise to 0 velocity, which you can get from these normal dynamic equations here. We also in class looked at the convective acceleration to show that the convective acceleration gives gravity, and so it doesn't matter how far down this goes, it'll always be falling at acceleration due to gravity, just like a weight would be as it dropped from your hand, for instance, my hand. There is no manometer question on the test, so you don't need the manometer rules. There is no conservation of mass question either on the test, but we know that we have a sign convention for those, which is useful to maybe review. A rate of change of density in a given volume, a rate of change of volume for a given density, So this would be pumping into a tire. This would be filling a bucket of water with incompressible fluid, and mass rate in and out have to balance each other. The mass rate is just the product of a volumetric flow rate, the product of sorry, that's not the volumetric flow rate. A volumetric flow rate, which would be a velocity multiplied by an area, and if you multiply that by density, you get a mass flow rate for all of these. Sign convention for these is that if volume or density increase with time, then that's a positive sign convention. Likewise, for mass rates of flow, if mass is flowing into the structure, it's negative. If it's flowing out of the structure, it's positive. And the reason for that is that if the velocity aligns with the direction of the outward normal, the dot product of that is 1. And if it's converse to each other, the dot product is negative. So that's the sign convention. But actually, I don't think there is a conservation of mass equation on the test. So it's free jets, Bernoulli, and conservation of momentum linearly and rotationally. Conservation of momentum is just Newton's second law, which is written in this form. It's written as the sum of forces multiplied by a mass flow rate and a velocity. This is a vector, so it's 3 components in the x direction, y direction, and z direction. Typically, you'll split it out so you deal with one direction only. And the sum of the forces acting in the x direction has to equal the sum of the product of mass flow rate and velocity in the x direction. The velocity in the x direction is relative to a static observer. That's not a very good circle. And so this is Vs, and this is equal to the velocity of the control surface plus the velocity of the jet relative to the surface. So if you substitute this into here, you end up with this expression. And so typically this would be done in the x direction or the y direction. Mass rate of flow is a scalar. It has magnitude but not direction. The velocities w and the control surface have magnitude and direction. If it's a steady problem, so the steady problems would be water hitting a vein. Actually, it wouldn't be. This wouldn't actually be steady. So if it's water hitting a vein, then the mass flow rate in is equal to the mass flow rate out. And if that's the case, then the amount of mass going across the control surfaces means that the product of velocity of the control surface and mass flow rate summed on all the surfaces is equal to 0. And so because that's the case, you can rewrite this equation for steady problems by getting rid of this component here. And so you can write sum of forces is equal to the product of low velocity across the boundary into the control surface multiplied by the mass flow rate. You have to remember your sign conventions. So velocities and forces would be positive in the positive coordinate directions. Mass flow rates into the system would be positive out of the system and negative into the system because the alignment of this with the outward normal. But for the velocity or the term W or VCS or VS, these terms are positive in the directions of the positive coordinate system. So this is a positive velocity, and a velocity out of here, well, actually it's written differently. A velocity out of here, V2, would be positive as well because it's in the positive z direction. Again, the mass flow rate is the product of the area times the velocity, which is a volumetric flow rate, times density. And so this is always true, that it's just W if it's a steady state problem. Mass rate in is equal to mass rate out. If it's unsteady, such as the case of the gas cylinder, mass is coming out of the system, but nothing is going into the system. So it has to ultimately deplete and go to zero pressure. And so for that reason, this is a non-steady case. And in that case, you need to include both of these terms into this. Otherwise, you don't get the right result. Okay? The final question is on rotational momentum, and so that's also a control volume. Typically, when we look at these, we look at a velocity out of the system. Since this velocity would be orthogonal to this, it doesn't have a component in the direction that's causing the forces. Again, we can define the flow rate out of the system as being a volumetric flow rate divided by cross-sectional area of flow. This is here. The mass flow rate is just the volumetric flow rate multiplied by the density of flow, as we've had before. Again, the sign convention is positive if it's out of the system, but the velocity has a direction. And so if you write a sign convention where this is the velocity of the fluid coming out, this is the positive velocity of the control surface, then again, the sum of those two equals the velocity relative to a static observer. This is always true. I think the example that in the book in class writes this as being U out, which is equal to the negative VCS. But so you can choose how to do your coordinate system or sign convention, I guess. So it's very similar to the conservation of momentum equation for a linear problem, except the force here is multiplied through by the radius of curvature, and so those both exist there. I'll get rid of those so those don't say. And if you multiply a force by a radius, it's a torque, and if you multiply this equation by a radius, you get this expression. Again, this is always correct. This gives you a velocity of the control surface, so this would give you the velocity at which this head would be moving, and if the velocity of the water is coming out like this, then the actual velocity of the head would be directed this way, but that would come out of the solution. And if you need to convert a velocity into a rotation rate, you divide the velocity through by the radius of rotation, and that gives you a value in radians per second. So radians per second is useful because it gives you a power, which is just the product of torque times the rotation velocity. This is always given by a velocity of the control surface divided by the radius, and so rotational velocity is proportional to the velocity. And this is important because if you look at the magnitudes of torque, if you're holding it static, which is this point here, this will give you the maximum torque in the system. If you allow it to rotate, it will rotate at the maximum rate. This will be this one here, and the rate at which it will rotate will be the maximum velocity of this, so these will be equivalent to each other. But if you partly hold it, so you're only staunching a portion of the torque, then you'll get maybe a portion of the torque, and this will give you still a rotation velocity. So the product of torque times rotation, I guess not this one, would give you this expression here. And so large magnitude of torque but zero velocity gives you zero power. Small magnitude of torque but a high rotational velocity gives you zero power because of this relationship. And the maximum will be somewhere in between those. So anyway, as before, I think this is all the material that you need. Every single equation you need on the test is here. Of course, you need to know how to use them. And so maybe going back to the material where we discuss some of these problems and work through them in class would be a useful thing to review to get yourself ready for the class. And again, this will exactly be the equation sheet that you receive for the tests. Same one for all three tests. Okay, thanks very much. Good luck.